Okay, well, thank you for the introduction. So the topic of the talk will focus on a low-wave acoustic sensor for cancer biomarker monitoring. So let me start with this little graph showing the 20 most commonly diagnosed cancers worldwide. So these figures are for 2008 estimates. And I've highlighted here the cancer of interest for this topic, which will be colorectal cancer, and it represents about 10% of the most commonly diagnosed cancer worldwide. So colorectal cancer is a malignant tumor, which means it can metastasize, and spread to other parts of the body. And you can see here some different stages of evolution of this cancer. So when a patient has this kind of cancer and it goes under therapy, health workers want to assess that the therapy is working well. And in order to assess this, you need some kind of information, which you can extract for cancer biomarkers, which can be found in urine. So urine is easily sampled from the patient, so it's kind of convenient to use. And among those biomarkers you can use, there is versatility, adenosine, or in this topic we will focus on the pseudouridine detection. So moving on to the generic sensor principle, in this conference I think it's not mandatory to mention this, but I will focus on what we want to detect here. So we are focusing on two biological targets. First, we are going to try to detect adenosine 5 monophosphate, AMP, as a proof of concept for our detection principle, and then focus on the nucleoside, which is pseudouridine. In order to do that, we want to use a specific recognition layer, which will be target-specific molecularly imprinted polymers, depending on the target we want to detect. And as the transducers, we will use some low-wave acoustic sensor. So to speak about the transducer itself, it's a very classic low-wave delay line principle. So the principle is to generate, using a piezoelectric substrate, an acoustic wave using interdigital transducers. And it will propagate from one IDT here to the other. And depending on what's happening on the surface here, you will modify the propagation of the wave in terms of velocity and attenuation. So our devices are made with standard microelectronic processes. So we start with an 80-cut quartz substrate. We do thermal evaporation of titanium and gold layers, and we we use a lift-off process in order to obtain the IDTs with a wavelength of 14 microns. As it is a low wave sensor, we have a guiding layer because it's a guided mode we are using. So we use a 4 micron thick SiO2 guiding layer on top of the structure. So in order to convey the liquids, we use a microfluidic setup, which is once again using some standard soft lithography processes. It helps us to confine the liquid in between the IDTs here and to avoid some non-wanted interaction with the IDT from the liquid. It also helps to decrease the volume and assess a laminar flow. So here you can see the measurement cell, which comprises some aluminum machine part and a PMMA glass cover here, which can help to assess the good sealing between PDMS and our sensor. And here you can see the full setup with a PCB SMA connector and custom electronics for real-time measurement of the device. So moving on to the recognition layer, we use molecularly imprinted polymers. So basically, it's a porous material that will replicate the target molecule form, including its shape, its size, and its functional group. So you mix together a target molecule, a cross-linker, and interacting monomers. And they will assemble into a complex, forming this complex, and after polymerization, you will have a rigid structure with a complementary shape of your target molecule. So you can process them to the extraction or rebinding of your target molecule. So these recognition layers are great because they mimic biological receptors. They can be highly selective. They can inherently be reusable because you have some reversibility of the reaction here. They can offer some long-term stability and shelf life, resistant to harsh environments, and it's kind of a low-cost process. So in order to make these MIPs, to process these MIPs on film forms, we use first a sensor surface preparation step. So remember we have a SiO2 guiding layer on top of the sensor. So we start with the piranha cleaning, rinsing and drying with nitrogen. Then we process to a silanization in order to have a good adhesion between the SiO2 and the MIP material. In parallel, you have the MIP solution synthesis processes. So you have different recipe depending on the target you want to detect. So here you can see the various components for AMP and for pseudouridine. So you have different porogen solvents depending on the target. Different interacting monomers which are specific to the target, and we use in both cases the same cross-linker. So you have also different mixing conditions that are appropriate depending on the recipe, and we use the same initiator for the final reaction. And then you have a MIP solution which is ready to use. So after that, we take 10 microliters of the solution, and we process the spin coating step with different parameters depending on the solution we are using. And finally, there is a UV exposure step in order to cross-link the polymer. So once you have your polymer deposit, which is cross-linked, you can characterize it. So here is the stylus profilometry of a step of MIP for IMP. So you can see here the thickness, which is about 500 nanometers. So it's in both cases. We have adapted the spin coating speed in order to get the same thickness for both. You can see there from this optical profilometer view of the MIP for IMP that we have like a macroscopic homogeneity of the film here, which is slightly less for the pseudouridine MIP. And you can see here from the scanning electron microscopy images that the two MIPs exhibits very different shapes. Here you can see the image for the MIP for AMP target, and here for the pseudouridine target. So very different shapes, mainly because we use different monomers, obviously, and different porogen solvents. But what is important for us is that we have, in both cases, a large specific area, which is really good for having a great mass sensitivity. So moving on to the experimental results now. We performed some recapture experiment, in the case first of the AMP target. So first we extract the AMP from the thin film using a bulk solution, so we dip it into a solution for extraction. After extraction, we place the sensor here in the measurement cell, and we use this kind of conventional setup with microfluidic components here to inject first a buffer solution and then the target molecule containing solution into the microfluidic chip. And we follow the oscillation frequency of the delay line, which is inserted in an oscillation loop. So we obtain those kind of curves where you can see here the frequency shift versus time. So we start here with the buffer solution, and then we inject the AMP containing solution at different concentrations. So you can see clearly some increasing frequency shifts depending on the concentration, obviously. And for the lowest concentration we have tested here for the moment at 5 ppm AMP, we obtained 150 Hz shift, which is quite small but still measurable for our electronic. Moving on to the real case scenario, which is for pseudouridine. We didn't have the time to perform some real-time experiments, so we used a standard virtual network analyzer characterization. So we are looking at the S21 transmission parameter here. So first, we characterize these S21 parameters before extraction of the pseudouridine target. Then we perform the extraction once again in a bulk solution. We rinse and dry the sensor, and we characterize the S21 parameter. And after that, we perform the recapture experiment, in that case with a 5 ppm pseudouridine. So we dip the sensor into this solution, we rinse and dry, and we characterize again the S21 parameters. So this gives us those curves with the phase plot against frequency here. So in red, you can see the reference curve, which is the coating with all the sites, the bending sites occupied by the pseudouridine template before extraction. And so after extraction, we obtain this large frequency shift here. So you have the curve after extraction, which is shown in green here. I hope you can see the colors here. So you have a strong frequency shift to about 40 kilohertz. So it's an increase in the frequency shift because as it is a mass effect, we have less mass on the sensor, so the wave propagates faster, and you have this positive shift here. And then we are ready for the pseudouridine recapture, the 5 ppm pseudouridine recapture, which you can see in blue here. And we obtain a 2.5 kilohertz frequency shift, which is sufficiently large to be measurable, so we can expect to measure even a lower concentration of pseudouridine. So, as a conclusion, we can say that we have successfully deposited two different MIP films on our low wave sensors and prove that it can be used as an efficient recognition layer. The obtained films showed a porous surface morphology, which is what we wanted. It's favorable to having a great mass sensitivity because of a very large specific area. The results have shown in the real-time configuration a sensitivity which can be estimated to 30 Hz per ppm in the case of IMP, and we can obtain like a 500 Hz per ppm in the case of pseudouridine. So there is still much work to do, as these are really preliminary results. But we will focus on the future works on the validation of the pseudouridine real-time detection. Then we will try to perform some real-time recapture extraction cycles in a microfluidic configuration in order to assess the reversibility of the process with the MIP. And of course, we will have to move on to the real samples and evaluate selectivity and sensitivity toward real urine samples. And with that, it's the end of the talk. So many thanks to all the colleagues which have collaborated for this work. I would also like to thank our financial support here and all the academic partners that have helped through this work. Thank you for your attention.